So for the stresses due to the shear force, we have much less flexibility in the allowable cross sections. All we have is rectangles where h over b big gives us better results, and circles only along the neutral axis. That's where the maximum shear stress occurs. No, nope. You have to approach that a different way. With bending, you could do that, but not with shear stress. Okay, and remember that in bending, the maximum normal stress is far from the neutral axis. In shear, max XY shear stress is at the neutral axis. So now that's going to make it a little trickier to talk about where the maximum stress is, you know, like where are we most concerned about something breaking, because, or where are we concerned about a fracture starting? Because if the thing starts to fracture in normal stress, in tension, say, it's going to start at a different place than it will if it happens in shear force, in shear stress. So before I give you the formula for shear stress, there's a mathematical preliminary I need to give you. And this is the value QY1. So this Q refers to, so what it is the first moment above the line Y1. And the way you calculate this is if you look at the cross section, so for any arbitrary cross section, this isn't one that we could calculate the shear stress for, but the neutral axis is somewhere. And if our line Y1 is here, then this is the value Y1. Now take all of the area above Y1 all this shaded region has an area A, and it also has a centroid C. And so for this cross section and this value y1, q y1 is equal to the area A times the distance yc. So it's not using this value y1, it's to the centroid of that area above y1. It is, no, it's a little different. Same idea. The parallel axis theorem has the y thing squared. Okay, so if you picture whatever your y1 value is, if you shade that region, you're just multiplying the distance to the centroid times the area. And one interesting thing about this value is in absolute value, and that's all we're going to care about. Q above y1 is equal to Q below y1. So in other words, you can define it this way, but if it's easier to calculate the area and the centroid of the region below that line, you can do the calculation that way and you'll get the same thing. Okay, so let me do an example and I'll show how to do the calculation and why, or at least one case where those two calculations are the same. So say that our cross section is this. Say this distance is 0.5. And the height is 1. Where's the neutral axis for this? How do you calculate the neutral axis? It goes through the centroid, that's right. So the centroid of this rectangle is right in the middle, so there's the neutral axis. And let's say that our y1 is 0.4. Okay. So the region for the area we're talking about is this. What's the centroid of this region? It's, yeah, so, I mean, I guess what I meant there, that question didn't make any sense, but the centroid we're looking for is the centroid of the shaded region. And so what matters to us is this distance from the neutral axis to here. That's our YC. The area of the shaded region, so that region is 0.1 times 0.5, so 0.05. Because we know that the whole distance is 0.5. Yep. And then what's our YC? Right. It's 0.4 to get to the bottom of this region, 0.5 to get to the top. So YC is 0.45. And so Q Y1 is equal to 0.05 times 0.45, and that's equal to 0.0225. 0.5 meters cubed. Any questions about that? Okay, so here's the other way we could have done this. So we could equivalently calculate it this way. So here's the shape. Here's the neutral axis. Our y1 is here. And now, instead of dealing with the centroid and the area of the region above y1, we're going to deal with this region. So the centroid is going to be here somewhere. The area of this region is 0.5 times 0.9. So you get 0.45. And where's the centroid? Well, it's going to be the average of positive 0.4 and negative 0.5. So YC is going to be equal to negative 0.05. That's just positive 0.4 plus negative 0.5 divided by 2. And so Q sub Y1 is equal to 0.0225 meters cubed. Well, it would have a negative, but we don't care about the negatives. So we got negative there, but if you take it in absolute value, you get 0.0225. Any questions about that? Okay, so now we're going to go on to the first cross section we can deal with. So this is shear stress due to a shear force in beams with rectangular cross section. And also remember, we need H to be bigger than B. So first, let's think about what's happening. So if this is the beam with the rectangular cross section, there's a shear force like this on the right side of the beam. That would be a positive shear force. And the resulting shear stress is in that same direction. So if this is V, the shear stress is like this. This would be T, X, Y, tau X, Y. If you think of this as being the right side of a stress element, then the stress element that this strip represents has an XY stress like this. You see that? I mean, that's just coming from the direction of these. And so what's the direction of the shear stress over here? This has to be up. And what is it over here? On top? Okay, so now this is to keep it in force equilibrium, right? But the problem is this is a couple and would make it rotate clockwise. So we need a counterclockwise couple on the top and bottom. So at the top it needs to be this way, and the bottom it needs to be this way. These are the values tau x, y. And notice so this picture shows a positive shear force. What's the sign of the shear stress, of the XY shear stress? Well, our coordinate system is like this. So on the positive X face, we have a negative, we have a shear stress in the negative Y direction. So we have a negative tau xy. Okay, so to calculate the value of that tau xy is equal to the shear force times the Q that we just talked about, divided by the aerial moment of inertia times the base B. And let me draw B on here. So the width is B. Okay, this height would be H. So this is the magnitude, and then the signs come from thinking about the physical directions based on the direction of the shear force. Okay. So in other words, if you have a positive shear force down like this, it means you're going to have a shear stress that's also down on the right side, and that means that you have a negative shear stress in the XY direction. Okay. Any questions about that? So what does this say about where the maximum shear stress is? Notice that Q is biggest at the neutral axis, and therefore tau xy is biggest at the neutral axis. Well, I should say the absolute value of tau xy. Okay, let's do a calculation. So let's say we have a let's say we have a cantilever beam and let's say the mass is 100 kilograms. And we want to know, well, first let me give you the cross section. So the cross section has a width of 0.1 meters, a height of 0.5 meters. The length of the beam, let's say, is 2 meters. And we want to know if this is the middle. We want to calculate the total stress of a point along this line at the midpoint between the neutral axis and the top. So what's the total stress tensor at all the points, at any of the points midway between the neutral axis and the top. And we also have to choose a location along the length because it's going to vary. These stresses are going to vary along the cross section, but they're also going to vary along the length. So let's do it at the midpoint. All right, so what's the first thing we have to do? The first thing we have to do is calculate the internal loads at this location along the x-axis along the beam, right? That's going to give us the V and the M that we're going to use to calculate the stresses. So first we need to calculate the tension, the shear force, and the bending moment. We can see looking at it there's not going to be any tension, but so what does this look like? Well, this length is, what was it, 1 meter. And the weight force is a distributed load. There's a total of 981 newtons. That's over 2 meters. So it's going to be a distributed load of 490.5. So this is 490.5 newtons per meter. And then there's going to be tension, shear force, and bending moment. Newton's second law. So if you represent that distributed load as a point force, that's going to be 490.5 x. And then you have these.
Why do we do the whole beam first? Why can't we just start at the cut right away?
Well, this is, since I know that we're doing the calculation at this line, we don't have to do a general cut. We are doing a cut. We're not doing the whole beam. We're just doing a cut right at the 1 meter point. You see what I mean?
You usually do like the whole beam with just the moment and the force on the right from the wall.
Right. We could do that to calculate the reactions at the wall, but since we're doing our cuts from the left, we can go straight to the cut without those.
That makes sense. Okay, thank you.
Yep. So we have 0, negative 490.5x plus t negative v is equal to 0. So t is equal to 0. V is equal to negative 490.5x. Yes, thank you. Right. That was just force of habit. So, in other words, so Rx is equal to 1 meter. So we have t equal to 0, v equal to negative 245 point, what's that? 245.25. Because usually we do this, and this distance is x, but our x is equal to 1 meter, because we're looking for it along this line. So I calculated it in terms of x, and then just, my calculation's wrong. Sorry. Okay, so v is equal to negative 490.5. Okay, and then rotational. So we have a moment arm of 0.5 on this. The magnitude is 490.5. That's a clockwise moment. So here we have negative 245.25 plus m minus v times x, which is 1. So m is equal to 245.25 plus v, and that's equal to negative 245.25. Okay, so now we have the internal loads. Those are the internal loads at this dotted line along the x-axis. What's the next step? If we're trying to calculate the stresses along this line at this point that we calculated V and M. So now what's the next step in finding those stresses? Yeah, so let's start with the stress due to the bending moment. So what do we need to calculate the bending moment? The stress due to the bending moment. That would be if it was a tension that we were dealing with, but with the bending, remember the formula that we want is this one, negative my over I. So we have to calculate that I. It's just a lot of, like the number of things you have to remember here starts to sort of sneak up on you, you know. Yeah, but still you have to remember like the steps. I mean, I guess, so what is I for this shape? It's the base, 0.1. Yep, times height to the third, divided by 12. So that is 0.1 divided by 96. Can someone calculate that? And that's rounded off, I think. And what's after that?
Oh, 1041.
Okay, 041. Okay, keep 4 significant digits there. And what are the units for I? Meters to the fourth, yep. Okay, so the XX stress due to bending is negative 245.25. Our Y value is from the neutral axis to here, so 0.25. Divided by I, 0.001041. And what do you get there?
Number?
Yeah, what is it?
58897.6945.
So how many 10 to the what?
The fourth.
Okay. Anyone else calculate that?
5.810, 5.886.
Yeah.
Is that the fourth? Yeah.
Okay. So that's tension. Does it make sense that if we have a negative bending moment there, that we'd have tension at a point above? Yeah, that's right. It bends down like a frown. And so above, and so above the neutral axis, those points are going to be in tension. Okay, so that means that our stress tensor due to tension is equal to positive 5.9 times 10 to the fourth, 0, 0, everything else is zeros. And the next thing we have to do is calculate the stress due to shear. And then what are we going to do when we calculate that? Well, we could, but to calculate the total stress tensor, we just have to add these two stress tensors together. Okay. Any questions? All right.